Okay, so here's what we were talking about last time. We were talking about this idea of path independence. Let me just remind you that path independence is a feature of the vector field. It's a feature of this thing that I haven't drawn in this picture. So let's momentarily draw, some vector field like this. So it's the vector field that has the feature of path independence. Now, what is the feature of path independence? Well, if this vector field, if you can say the following about it. So if it is true that for every path between A and B, if you always get the same value of the corresponding line integral for, fixed A and B. In other words, if the value of a line integral of this vector field only depends on the start and end of the path and not the path itself. If the value of the line integral of the vector field is independent of the path and depends instead only on the endpoints, and we say it's path independent. So it's pretty plausible terminology, I think. And we talked last time about how the fundamental theorem of line integrals pretty much immediately demonstrates that all gradient fields are path independent. Right? I mean, there's the formula. Completely independent of what this path is, the value of this line integral can be computed based on only knowing the endpoints. Therefore, it doesn't matter what path you take. Okay. All right. So, again, I think it's, until you see this, until you make this realization that there's some sort of immediate, freebie path-independent vector fields, until you make that realization, I think an initial glance at this property, this definition of path independence, makes it seem like it's almost unachievable. I mean, how could a vector field satisfy all of these curves in exactly the same way all at the same time? It seems unrealistic. But anyway, so there it is, path independence. So again, we saw last time all gradient fields are path independent, which brings up the question, is that all of them? Or maybe could there be other vector fields that aren't gradients that are also path independent? And the answer to that question is no. Not only is every gradient path independent, but every path independent is a gradient. This asterisk, this is, both of these are conditional on regularity. So we need to know that everything in sight is appropriately continuous and differentiable. And again, I don't want to focus on that kind of stuff in this course. But anyway, just asterisk. Okay, so as long as there's nothing weird going on, in other words, these ideas, the idea that a vector field would be a gradient of something, and the idea that the vector field would be path independent, these are the same idea. Well, they're the same referring to the same vector fields. Okay. All right, so that we summarize by observing the following. We already knew that every gradient had curl equal to 0. We still don't know why, but we knew that, right? That every gradient has curl equal to 0, and everything with curl equal to 0 is a gradient, right? That was what I like to call lifetime theorems that we talked about way back in 15.1. Okay. So what we see now is that gradients are simultaneous with path independence. Every gradient is path independent, and every path independent is a gradient. Again, regularity assumed. So what that means is that we have 3 completely different, what you might call properties, 3 different algebraic definitions, you might say, right, that happen to always be simultaneous. So the vector fields that satisfy one of these conditions are exactly the same as the vector fields that satisfy the other ones. Again, with regularity assumed, and that's a surprisingly big deal, but it's not what we're going to talk about in Math 212. Okay. All right. So let me show you how you can make some use of path independence sometimes. So suppose you want to compute this vector line integral, and the vector field is given, and the curve is given like so. So we have this given vector field, and the curve is the top half of the unit circle oriented clockwise. How do you compute that thing? Well, of course, you can plug and chug. Okay, so here's how you would use path independence instead. Take this vector field and observe that the partial of q with respect to x minus the partial of p with respect to y, right? Green's operator gives you 0. Okay, now coming back up here, what I forgot to write down, mental note didn't suffice here. So this is the 2-dimensional version. Let me write down the equivalent 3-dimensional version, and that is a vector field is a gradient if and only if Green's operator is equal to 0, which is if and only if path independence. Okay, so what we just checked on the previous page is that this vector field we were given, Green's operator is equal to 0. And that tells me immediately that this vector field on the next page is path independent. So that's a pretty big conclusion that this is path independent. What that means is this vector field here, right, has the feature that no matter what curve I pick, as long as I don't change the starting point and the ending point, obviously, got to keep the starting point and the ending point fixed. But with the starting point and ending point fixed, I can wiggle that curve around however I want. It doesn't matter. Change the curve to whatever curve you like best. And it's not going to change the value of the line integral because this vector field's path independent. Okay, so, all right, good deal. Here's my curve. Top half of the unit circle oriented clockwise. That's that curve. By virtue of path independence, I can change this to any curve I like as long as it starts at the same point and ends at the same point again. Got to stick with that. So I'm going to pick, let's see, if I've got to start there and end there, I get to pick any path I want. I suppose I could pick this path, but why would you want to, right? Think lazy, right? What's going to make your life the most convenient possible, the easiest curve to get from the starting point to the ending point? Straight line. In this case, I think is a pretty reasonable sort of lazy motivated choice. Now, I will note that there are some examples where what actually is going to make your life easiest is not a straight line, but some other cleverly chosen curve. And yeah, sometimes, right? But usually not. Usually the straight line's the easiest choice here. Okay, so we're going to evoke path independence. We're going to change to that curve. And we're just going to pretend that that's what the question asked. And it's not going to affect our answer. So, legal. All right. Okay, so, by the way, this new curve that we've got, notice that y is equal to 0 everywhere on that curve. And let's go back up here to where we can see our vector field. Everywhere on this curve, everywhere on that curve that we're now using, not the original curve, of course, but our new curve, y is equal to 0. That means that throughout the calculation of this line integral, y is always 0. I'm going to stick that right into there because it is. I'm going to plug in y equals 0 because y is 0 for every point on this vector field I now at this point care about. And so the vector field simplifies to that. Right, which I can draw a picture of right there. Always straight vertical. Now, it's sometimes longer, sometimes shorter, sure, right? But it's always pointing straight up. Okay. So the vector field's pointing straight up. Of course, notice that all my dx's, as I move along this curve, all of those dx's are parallel to the x-axis. The vector field's perpendicular to the x-axis. We have our geometric good fortune that we're always on the lookout for. Dot product's clearly 0. Right, again, so the vector field dot dx, the dot product is 0, and therefore the integral is 0. We're adding up a bunch of zeros, and we're done. Everybody happy? Didn't have to parameterize. Okay, yes?
How did you know that the vector field was perpendicular to the x-axis?
Yeah, so from the fact that y is equal to 0, this first component becomes 0, and there's my vector field, right? You're comfortable with that part? Okay. Mm-hmm. So it's just a matter of now looking at, what direction does that point 0, x squared? That means there's no x component and there's only a y component, which means the vector field is pointing straight up, and straight up is perpendicular to the x-axis. Yeah. Okay. All right. Now let me trash my own example. Now, so this works, and that's fine. But the way that this argument worked came from invoking path independence. How did I get the path independence? Well, I got the path independence by checking that Green's operator was 0. And here's the thing. If Green's operator is equal to 0, that means that, in fact, the vector field is a gradient. I really, really easily could have found the anti-gradient and just used the fundamental theorem of line integrals. Right? So, I guess the path independence argument works. I guess that's fine. I'm not clear that this is easier than just using the fundamental theorem of line integrals. Right? So, roughly speaking, my point here is that as a computational tool, path independence is, I don't know. It's not super powerful. Any situation where path independence is going to come up, any situation where you could have used path independence, you also could have used the fundamental theorem of line integrals. So the path independence is a nice tool, but it's a nice tool. It's a nice screwdriver, but we already had a nice screwdriver. Right? So it's not clear how much that's really worth to us in that sense. Okay, so again, as a computational tool. Let me remind you, though, computing stuff is not the only thing that we're interested in. Right? We're also interested in ideas. Certainly just as a concept, path independence is pretty different as a concept from the idea of being a gradient. Right? And as a concept, it's actually really useful. So here's an idea. Here's an application of path independence to physics. It's a very important application to physics. I wish I had known this when I took my first, mechanics class. Physics. So physics 151, I guess it would be here. So those of you who have had physics 151 are aware of the idea of conservation of energy. This is not in the sort of green ecological sense, right? But in the kinetic energy plus potential energy is a constant sense. All right, so the neat fact, if you haven't had such a physics course, here's the idea. If I hold this pen up here, it has this invisible form of energy called potential energy, right? The idea of the potential energy is that if I were to just let go of it, all of a sudden, I don't want to drop this thing. This is like $50. But if I were to drop it, right? I don't trust myself to catch it. If I were to drop this thing, then it would start hurtling downward. This energy is just coming out of nowhere. Where did that energy? It's hitting my hand with going a significant speed. Did that energy just come out of nothing? No, right? The idea is there was a certain amount of potential energy. We assert the existence of this thing called potential energy, and the kinetic energy that it has right before it hits my hand came from the potential energy that I assert was there in the first place. Right? So grand total, the total amount of energy doesn't change. It just sort of converts from potential to kinetic. All right. So that's the idea of conservation of energy. The idea of conservation of energy critically relies on the existence, the ability to assign a significant meaning to this idea of potential energy. Okay, fine. How do we define potential energy? Well, here you go. Here's a definition. If you want to define how much increase is there in potential energy, then from a point A to a point B, what's the potential energy difference there? It comes from, how much energy does it take to move along a path from one to the other? By the way, the amount of energy it takes to perform a task, sometimes called work. Right? So what we need then, in order to define potential energy, is potential energy change is a line integral from a fixed point to another fixed point. Well, it better not depend on the path, right? How could I claim that there is a well-defined notion of potential energy at the point B if these two line integrals are different? If the two line integrals are different, then given a certain amount of potential energy at A, how much increase is there to B? It's not a well-defined thing. It depends on which path you pick. It becomes undefined. Right? So you cannot define the idea of potential energy without the vector field, this vector field, right, our gravitational force field, without that being path independent. Right? So anyway, I think this is a neat little connection to make, that the idea of conservation of energy, a tremendously powerful idea in mechanics, that idea of conservation of energy depends on the idea of potential energy, and potential energy depends on the idea of path independence. Right? Most directly. So that's a pretty neat application of the idea. We didn't just compute anything. Right? This is not a compute where the answer is a number in the box at the bottom of the page. Right? This is a concept that relates to other important concepts. So anyway, very often this is the value that ideas have is how they connect to other ideas. Okay. All right. So here's our again in R3. Here is our little trio of simultaneous concepts. Being a gradient, the same as the curl being 0, which is the same as being path independent. So let's talk about the terminology a little bit. This feature of F is, you might say, the feature of being a gradient, because look, it says right there, F is gradient, right, of some other little function. Okay. What would we say about this feature? Well, this F is, path independent. The word's right there. Right? Physicists have a different choice for how to refer to this property. And this is fine. This is just kind of a, personal choice. But this being the, sort of an alternative version of the property that's necessary in order for there to be a notion of conservation of energy, physicists will refer to a vector field that is a gradient as being a conservative vector field. The idea this is a vector field that as you move through it, computing work, you can generate this idea of something being conserved, namely total energy, namely kinetic plus potential energy. Right? Conservative, you're going to see that a lot, especially as engineers. So the notion of a conservative vector field is exactly the same as the notion of a gradient field. Everybody on board? Keep in mind, all three of these words mean exactly the same thing in terms of which vector fields. They're all different concepts, but they all refer to exactly the same vector fields. So heads up, when you see path independent, you should immediately think, hey, that means this is also a gradient. That means that this relates to some notion of energy in which there's this idea of conservation of energy. So there is I should use a different color for this one. Here, let me do this one in yellow. So there is a fourth, what does it mean for a vector field to have this property here? I haven't been able to tell y'all yet what curl means. Right? Exactly what, how to visualize curl. It's a formula, right? The book gives you the formula. But what does that look like? What does it feel like? It's going to turn out, let me just go ahead and sort of spoiler, for 15.7. Turns out that curl represents the extent to which the vector field represents a fluid kind of flowing around. There's a twisting, you might say a curling of the fluid or something. That's where the word curl comes from, approximately. Right? That's the motivation. So what word would we use to describe a vector field whose curl is 0? Well, a vector field in which the extent to which the fluid is rotating around something is 0. So the fluid is not rotating around anything. And so another common choice of words, irrotational. Right. Now again, why that's a reasonable choice for, why does curl represent this, thus motivating this terminology? We'll have to see that in 15.7. So it's a little ways off. Okay. Anyway, so 4 terms that all, as far as you're concerned, mean the same thing. Right? They all refer to the same vector fields. So heads up, if somebody tells you in your engineering futures or whatever futures, if you see that a vector field is irrotational, you got to remember that what that means is that it's path independent and that it's a gradient and that it's conservative. They all mean the same thing. Okay. All right. By the way, another little bit of terminology y'all have already heard me use for the function whose gradient is the given vector field. I've already used the term anti-gradient. I feel like that's just extremely easily motivated, right? It's just the exact same motivation as the term antiderivative. Could not be more natural, in my opinion. Anyway, in physics circles, they don't use the word anti-gradient. They use the term potential function because, ignoring an issue of minus signs, that function whose gradient is the vector field, the force field in question, that function is the potential energy function, as it turns out. Okay. All right. So anyway, so be aware of these two terms as well, meaning pretty much the same thing. Okay. All right. Moving along. We're going to extend the theorem again in another context. We already did something pretty cool if you think about it, right? We already took the idea of the fundamental theorem of calculus, and we made took a certain point of view on the fundamental theorem of calculus and decided to, hey, let's just kind of copy off of our own previous work here and presto, new theorem, fundamental theorem of line integrals. We stole the fundamental ideas and made a new theorem. Right? That's already pretty darn good. We're going to do it again. This next one's going to be weirder, quite a bit weirder. The big difference between these is, context. I mean, the fundamental theorem of calculus is where you're looking at a one-dimensional integral in R1. Fundamental theorem of line integrals, you're looking at one-dimensional integrals still. It's just that they're no longer intervals on the number line. They're intervals, well, not intervals, but they're curves in space. But they're still one-dimensional things. It's just that we allow them to bend around in space now. All right, so context is different, but it's really the same idea. We're keeping track of change, and we're noticing that accumulates as you go along the curve, interval, whatever, and going life from there. Okay. So let's take a moment to recognize, what were these common features. We're looking at change in both of these theorems. F of B minus F of A. We're thinking of change as being a kind of a stuff. It's an accumulating stuff, right? That's a feature that not every object of potential interest has, right? Centroids don't have that feature. Lots of other things don't have that feature. Right? So change of a given value of a function between the endpoints of an interval. Accumulating quantity. Okay. By accumulating, we mean that the amount of this quantity that we associate to the whole thing is the sum of the amounts of this quantity that we associate to each little piece. Okay. All right. So let me draw a little bit of a picture here. Given an entire interval, the change that we associate to that interval is the sum of the changes that we associate to all of these intervals that make it up as you go along. Okay. All right. Next observation is that in order to turn the result into an actual integral, this thing here I had to interpret as a density times a size. Right, so the amount of change, here I'll draw the picture again, the amount of change that you have, you're looking at the fundamental theorem of calculus, here's a curve, and you look at some little interval, here's your A, here's your B. the total change, right? The total change is the sum of all of these little changes. But that little change, that little change you can think of as relates to the derivative, in that change per unit size gives you the derivative, and the derivative is the density. Right? Okay. So again, we tend to think of derivatives as slopes and slopes as rise over run. Let's reinterpret everything as, instead of rise over run, think of it as change per unit size, and thus you can reinterpret it as density. Okay. All right. Okay. So what we're going to do now is we're going to try to do something kind of like this in a dimensionally different context. No longer over a one-dimensional domain like an interval or a curve in space or whatever. Those are all one-dimensional. Curves are one-dimensional. Can I come up with some concept of something accumulating over a two-dimensional region? Some mathematical formula that I can write down that has the feature of accumulating over a two-dimensional solid, something that's defined, that's computed on the boundary of the two-dimensional region, but that actually accumulates over the interior of the two-dimensional region. All right? And so this is going to be tricky. It's all a matter of making the right choices. You make exactly the right choices, and then hopefully everything will just kind of fall together and just kind of be, different details, but morally sort of structurally equivalent to our previous ripoff of the fundamental theorem of calculus. Okay. All right. And then likewise, will there be a corresponding notion of density? Okay. By the way, the answers to these questions are all yes. I wouldn't be taking you down a failed wild goose chase, right? So you probably guessed. All right. So here's where we're going. So the domain, again, now a two-dimensional thing. So some sort of a solid region in two dimensions like this. Now I'm making this seemingly weird choice of region that has a hole in it just because I can, and because we need to know how to deal with such a circumstance. But so there's my region. I'm interested in, again, finding some quantity that's computed on the boundary, but that actually accumulates over the interior. So let's talk about what is the boundary, right? With an interval on the x-axis, an interval has an easy boundary. This interval here, the boundary consists of those 2 points, right? And that's where change is computed. Change is f of b minus f of a. Change is computed on the boundary. Right? So what's the boundary in this context? Well, the boundary, no surprise, is, it's a curve. Well, in this case, it's actually two curves because there's an inside as well. That's the boundary of our green two-dimensional region. Okay, now it turns out we need a little bit more than that. It turns out we need to be able to talk about the oriented boundary. There needs to be a well-defined direction. You're going to see why momentarily, but I need for there to be a well-defined direction. So which direction do we go along these boundary curves? There is a common mistaken belief, misconception. There's a single word that says it. There is a misconception that you always go counterclockwise. This is not true. You always go, the direction, the orientation that you pick is always in the direction such that as you go in that direction along the curve, the region is on your left side. The solid region in question is on your left side. So now I think I can probably persuade you that as you're going around the outside boundary curve, which way do you go such that the green region is on your left? Well, yeah, it's counterclockwise on the outside boundary. But notice it's not on the inside boundary. On the inside boundary, you got to go clockwise to have the solid on your left. Everybody on board? Okay. And then you could, oh yeah, go ahead.
Is there a reason for that?
That's just how geometry works. I mean, there's the reason. The picture is the reason. It's just fundamental to the geometry of space. There's no more fundamental reason than I can give you. Yeah. By the way, there are even weirder regions. I mean, what if the region were something like this with a little island in the middle? Right. Well, oh my gosh. Okay, now there's just several. There's that part of the boundary curve. That's going counterclockwise. Then there's that part of the boundary curve. That's going clockwise because, again, that puts the region on my left. And then there's this one here, and there it's back to counterclockwise again. Right? And then you could speculate, well, what if there was a hole inside of there? Right? Well, the unifying rule is always go in the direction such that the region that you're going around the boundary of is on your left, and emptiness is on your right. Okay. All right. Okay. So what is this quantity? Right. Keep in mind what we're trying to rip off. We're trying to rip off this idea that there was we have a region with a boundary, and then on that boundary there's something that we're computing. What thing are we going to compute? When we were looking at intervals whose boundaries were 2 points, on that boundary we were computing change, right? F of B minus F of A, and it just worked out that in fact had the feature of accumulation. So what are we going to be computing on these boundaries? Given that boundary, and that boundary, what am I going to compute? What thing will have the feature of it accumulating over the interior of the solid? Not at all obvious that there is an analogous thing. But there is, and it turns out oriented boundary vector line integral is the thing. It's going to take me a little bit of while to persuade you that this has this accumulation feature, but I claim that this is the new object of interest. So with the fundamental theorem of calculus, fundamental theorem of line integrals, we were talking about how change accumulates over the interior of the region. For Green's theorem, we are no longer going to be interested in change. Change is not relevant. The boundaries are no longer 2 points between which we can talk about change. The boundaries are now curves. And vector line integrals along these oriented curves are going to be the object of interest. This is what we're actually going to be computing. Okay, now I'm going to procrastinate for a few minutes, persuading you that this is an accumulating quantity. First, I want to persuade you of how we're going to describe these things. So here is a region, a two-dimensional region here, and here's what the boundary curve looks like. Again, keep in mind the orientation following the rule. By the way, it is a lot easier in practice to say counterclockwise than it is to say in the direction such that the solid is on your left, right? So I'm very often going to say counterclockwise, but just I hope I've been sufficiently clear that it's not always counterclockwise. It's always so that the region is on your left. And in cases like this where it's exactly the same thing, I'm going to save myself several syllables and just say counterclockwise. Okay, so what is a vector field over this boundary curve? What does that represent? How might I think of that? And here's the idea. I'm going to think of the vector field as representing the flow of a fluid. Just imagine that there's a fluid flowing around like this. I'm just going to, highlight a few of these arrows. So these green arrows represent a flow field, right? Remember, that's one of our interpretations of vector fields. Not all vector fields should be thought of as representing forces. Here, it's not very useful to think of this vector field as representing forces. We want to think of this as representing a flow of a fluid. All right, so for the rest of this section on Green's theorem, think flows of fluids. Okay, so from the flow of fluid point of view, what does a line integral represent? Well, remember we have these two formulas. Well, let me just go straight to this one. This formula here for perfectly equivalent to a vector line integral. It's the component of the vector field in the direction that the curve is going, and then added up over the entire curve. And the point of view that I gave then on the total integral was, well, then we're sort of adding up, along each piece of the curve. We're looking at how much is the fluid flowing along the curve and adding that up over the entire curve. Well, here's the thing. The curve starts off going that way, and then note the curve makes a turn. Right? The direction that the curve is going makes a circle. Right? So if we're measuring with this integral, to what extent is the fluid flowing along the curve, and if the curve is making a circle in its direction, then this integral is, among other things, maybe to some extent measuring the extent to which the fluid is also going around in a circle. Not exactly a circle, but making a sort of a loop. Right? So the term that we use for this is circulation. Very common term, extremely natural, I think. So this is terminology I'm going to use here. Again, the accumulating quantity of interest is the line integral around the oriented boundary. Sure. But it's a lot easier to say circulation. And by the way, I don't know if y'all had the same experience growing up as I did, but when I was a kid, my dad was constantly insisting that certain doors in the house be left open and certain other doors be left closed. And there was always this nebulous, to me anyway, nebulous discussion about, it's for circulation. Did y'all ever get that? No? Some of you did. Okay. All right. That's exactly, it now makes perfect sense to me. I didn't understand it at the time. I guess he knew multivariable calculus, right? But the air... the way air conditioning works, right, is, here's your house, and there's air ducts and stuff up here, and air goes into an intake, and then it goes through the air conditioning system where it turns cold, right? And then it comes out of the outputs. I'm sure there's construction terminology for all these things that I don't know. But air goes in there, and it comes out there. And the point is, you need the air to be able to continue to do this for the air conditioner to work, right? If you don't let the air flow around, doesn't matter how cold it is in your attic, where your air conditioner is, or wherever it is. Right? You need to be able to have there be a flow of a fluid, namely the air, in your house, and that fluid needs to circulate in this sense. So, anyway, it was very satisfying to me to finally see this in a math class, and that's what he was talking about. Okay. All right. Okay, so circulation is the object in question. Now, does circulation accumulate? I have 1 minute. I'm not going to be able to finish this, but I want to start the process. I'm going to start off with a very simple region. So we're going to talk about this region here, that two-dimensional region, and I'm going to break it up into two sub-regions. There's sort of this piece, if you will. And then there's this piece. Right? And you see that the yellow is the union of the green and the blue. Right? And accumulation, keep in mind the idea of accumulation is that, the quantity in question, we need for the quantity associated to the yellow, the union region, to be the sum of the quantity associated to green plus the quantity associated to blue. So now, what are these quantities? I mean, if we were asking about mass, there'd be a perfectly obvious right? The accumulation feature of mass is that the mass of this whole thing is the sum of the mass on the left plus the mass on the right. Well, of course it is. Right? So, anyway, but now we want to apply that to our new idea of an accumulating quantity. Circulation around the boundary is our new allegedly accumulating quantity. So I would need to know that the circulation around the boundary of that piece plus the circulation around the boundary of this piece, I would need for the purple line integral plus the red line integral to equal to the blue line integral. Is purple plus red equal to blue in this case? Well, notice they have a lot in common, right? Along in here, the purple and the blue are doing exactly the same thing. And then over here, the red and the blue are doing exactly the same thing. The big question then is what's going on? What's going on over here? And what you'll notice, the key idea you'll notice here is we have two line integrals. We have a line integral along that sort of shared edge in that direction. Then we have another line integral along the exact same shared edge, just going the other direction. And recall from 15.2, I guess it was, when you take a line integral on a curve with the opposite orientation, you always get the exact negative value. So the point is, even though there is this line in between, we're going opposite directions. Red and blue or red and purple are going opposite directions along that shared line, and so they cancel. They disappear in a puff of smoke, and you can see the algebra here. So we'll hit that idea again next time. See y'all later. Have a good Monday. Oh, hey, I have homeworks to return. If you want to stick around for a minute, I can return homeworks.